Today we're going to go over Sn2 reactions. I'm going to begin by giving a brief overview, then I'll dive into the mechanism and transition state. We'll also discuss the steric effects and how the leaving group is going to affect the rate of the reaction, and then we'll finish off with some practice problems. So Sn2 stands for substitution nucleophilic bimolecular. What happens in this reaction is you have a nucleophile that enters the substrate and bonds to that carbon at 180 degrees from the leaving group. This causes an inversion of that carbon, that reacting center, and the stereochemistry switches. So if you initially had an S enantiomer, you'll end with the R enantiomer. This takes place in a single step, so there are no intermediates. And that 2, which stands for the bimolecular, means that both the rate of the substrate, the concentration of the substrate, as well as the concentration of your nucleophile are going to affect the rate of that reaction. So how does the reaction occur? Where you have your nucleophile and you have your substrate shown here. Your nucleophile has the negative charge on it, and that's going to attack the reacting center, which is the carbon attached to the leaving group. It's going to attack at a 180-degree angle. The transition state shown here illustrates this, where you have a dotted line that's showing the bromine leaving and a dotted line that shows the hydroxy group adding on to this carbon center. Both your leaving group as well as your nucleophile have a partial negative charge in this transition state. When you have your final product, you have your leaving group that's gone, and you have your nucleophile now bonded to that carbon. As you notice in the beginning, we started off with the S enantiomer, and then we had an inversion of the stereochemistry and finished off with the R enantiomer. Here's another diagram to illustrate that transition state. Here we have our nucleophile with its electron density on it, and we have our substrate shown here. The leaving group is partially negative as well, and then you have your carbon with the partially positive hydrogen on it as well. So your nucleophile is going to attack this carbon, and you're going to have your transition state where both your nucleophile as well as your leaving group have the electron density on them. The carbon is still partially positive. Finally, your leaving group falls off, and now you just have your nucleophile bonded to that carbon. If you notice in the beginning, your substrate was pointing to the right, your substrate was pointing to the right, and at the end it's pointing to the left, and this kind of indicates how you're going to have an inversion of your stereocenter. So there's a few things that influence the reactivity of an Sn2 reaction, and one of those things is the steric effects. If you look at this reacting center, the carbon that has the leaving group on it, this one has only hydrogen on it, so it is very easy for the nucleophile to attack that carbon and knock off the leaving group. When you add another substituent onto that carbon, for example, a methyl group here in bromoethane, it is a little bit more difficult for the nucleophile to get to that carbon center. However, it is still very possible because you still have 2 hydrogens here and those are not large. As you increase it and move to a secondary alkyl halide, it is even more difficult for your nucleophile to attack and to lose your leaving group. And with tertiary, it's the most difficult and very unlikely to happen. So you notice these methyl groups here are preventing us from even seeing the carbon that is your reacting center, showing that a nucleophile has a hard time reacting with that carbon and knocking off your leaving group. This again influences the reactivity, where something that is tertiary has more substituents on that reacting center is much less likely to react than something that is secondary, something that is primary, or something that is methyl, which is even 2 million more times reactive than a tertiary substituent. So again, the less things you have, the less substituents you have on that carbon center, the more likely you will have an Sn2 reaction. The leaving group also influences the rate of that reaction. There are some things that are good leaving groups, such as bromine, iodine, or tosylate groups shown here. They're much more reactive than other things that are hydroxyl groups or strong bases that are not good leaving groups. Things on the right are more likely to be able to delocalize that negative charge and move away from your substrate as opposed to things that are on the left shown here. So as a recap, your Sn2 reaction has inversion of your stereocenter. Your nucleophile comes in to attack the carbon, your leaving group comes off. This is favored if these R groups are hydrogen as opposed to carbon. Having hydrogen there as a methyl or primary or secondary are much more reactive than having tertiary, which is not likely to react at all. And lastly, your leaving group plays a large role in the Sn2 reaction. The better leaving group you have, the more likely that reaction is going to occur. So now we're going to go over a few practice problems using 1-bromobutane, 2-bromobutane, as well as 1-bromo-2-chlorocyclohexane. I'm going to switch to the dot cam so that I can show you the mechanism. All right. So here we have bromobutane. This is a primary alkyl halide, and we have our potassium hydroxide. In this case, we have K+ and OH-. Our OH- is our nucleophile that's going to be attacking the substrate shown here. This reaction, again, is a 180-degree attack where this hydroxy group is going to attack this carbon here. And in the same step, the bromine is going to, the electron density is going to move from this bond onto that bromine, breaking the bond. As a result, we're going to end up with an alcohol. So we did an Sn2 reaction where we substituted our hydroxyl group for the bromine at a primary carbon. Let's do it again on number 2. In this case, we have a secondary carbon. We have 2-bromobutane. Our nucleophile is still the same. So this is going to attack at a 180-degree angle and knock off our bromine. We are again going to end up with an alcohol. However, this one is going to be slightly different. Because this is a stereocenter here, and Sn2 reactions have inversion of the stereocenter, our product is going to end up on a dash. In this case, we have S2-butanol. The stereochemistry has changed from R to S because of inversion of the stereocenter as a result of the 180-degree attack of this Sn2 reaction. Let's do one more. In this case, we have the exact same nucleophile, potassium hydroxide, where our hydroxide is going to attack this reaction. However, here we're saying that we only have one equivalent of it, which means for every one of these, we only have one molecule. So we have to determine whether this reaction is going to occur at the bromine or occur at the chlorine. This is where the reactivity of the leaving group plays a role. Bromine is a much better leaving group because it is larger, able to delocalize that charge better than chlorine. So this reaction is going to occur at bromine, which is a better leaving group, and not at the chlorine. Again, if you're curious about what leaving groups are more reactive, refer to that reactivity arrow. As a result, the stereochemistry of our chlorine does not change. But at the carbon where our bromine initially was, we have changed our stereochemistry. Again, the stereochemistry of the chlorine is still the same, that is still R, but now instead of having S, we have R at this carbon where the reaction actually took place. And we still have our other products. So I've just gone over Sn2 reactions with you. Just want to remind you that some of the things that are important are the reactivity of your leaving group, as well as the sterics to have an Sn2 reaction take place.